Okay. Last time we were talking about rotational wave functions, and we were talking about quantized angular momentum, and we started talking about systems in three-dimensional space. So we're going to have to start integrating in 3D space. So let's talk about the integration of spherical polar coordinates. Okay. So before we go into complicated stuff, let's start with simplified stuff. What is d tau for a 3D system?
Same.
So when we're talking about a three-dimensional system and we want to do an integration, what does d tau become? Or what was it for a 1D system?
Just dx.
Yep,
Or
dx.
one
So what is
variable.
going to be for a 3D system?
dx dy dz.
Yep. Okay, so now let's talk about spherical polar coordinates. So what about in polar chords?
So dr, d phi, d theta.
That is, we do have that. We got some extra stuff tossed in there though. dr, d theta, d phi. We also have an r squared and a sine theta that get tossed in. Why is that? You can show some really complicated algebraic terms to get to this point. That takes an entire class. I really don't want to spend an entire class on that. Is everybody okay with that?
Oh man.
Yeah, Tara looks like she might want.
Yes.
Yeah.
Yeah.
I
Really
love
want me to? All right, here we go.
Let's get right into it.
Yeah. So this is the volume element we're talking about. We're talking about basically a chunk of the sphere. So we're talking from the center out. That's our R. Up and down, we go from 0 to pi. That's, whoa, spider just fell down. There we go, get out of here. Sorry. So we have up and down. All right, so R, theta, phi, right? Phi goes around that way. So along that way, that's theta. And then phi is going along this way. All the way around.
Sorry, is that going from 0 to the pi?
Yep, so it's going all the way, yep, it's going from 0 to pi.
Gotcha.
And then phi is going all the way around the circle. Okay, so let's talk about our integration limits. If one integrates R, what are we going to go to for R? Or what are we going to go to for phi? And what are we going to go to for theta? Anyone have a suggestion?
Maybe 0 to r for the r there.
Theta would be 0 to pi.
Yep, theta is 0 to pi. R, we're going to start at 0, but remember, we're going to talk about a 3D system. Previously, we were saying wrapped on a sphere. Now we're going to say it can go beyond the sphere.
Infinity.
Yep. Because we're eventually going to talk about atoms, and atoms' electron density can extend for really far. What about phi? If we're going all the way around a circle.
0 to 2 pi.
Yep. There we go. Then if we take an integral, the integral of some function that depends on r, theta, and phi. Okay. How many integral signs are we going to need?
3.
3, yep. We'll do r, and r is going from what to what?
0 to infinity. 0 to infinity.
Mm-hmm. Then we have theta, and that's going from what?
0 to 2 pi.
Oh, 0 to pi. Phi is the one that's going
Oh,
from.
I'm doing it that way.
Yeah. Sorry, I switched the order on you.
Why are we doing it that way?
Why are we doing it this way? Like the way that it's organized?
Yeah, why not phi 5?
Oh, we could do it the other way.
Oh, okay.
Yep. It's all whatever way you want to go with it. I'm just doing it this way because I set up the function that way, but you can organize it in any way you want.
Okay.
Then we have f, r, theta, phi. What else do we need in here for this integral?
Tau or d, whatever 3 things you want.
Yep, so we need dr, d theta, d phi.
Would
Is
have
that
the
it?
R squared sine thing?
Yep. Perfect. Okay, now let's say r is fixed. Then our function only depends on theta and phi. What's our integral going to become?
You would get rid of the r squared and the r integral.
Yep. So we're left over theta, phi, f of theta, phi, sine theta, d theta, d phi. Okay. So we're going to utilize these integrals in a moment. We're going to look and we're going to try and confirm that a function is normalized. Am I okay to move this up?
Yeah.
Mhm.
Okay, so we're going to go back to those spherical harmonic functions. We want to confirm that y11, which depends on theta and phi, is normalized. Okay, so how would you go about this problem?
You'd have to know what the wave function is, but then you would just do the simple normalization test.
Yep, so we got to figure that guy out, right? What are these numbers?
Quantum
They
numbers, or are they
correspond.
representing to
Yep,
Theta and then phi.
they don't represent theta and phi. What do they represent?
principal
L and
quantum
ML?
number? And,
Not principal quantum number in this case.
Is this
angular momentum.
angular in the
Yeah.
spin 1 and 1? So like L and then ML.
Yep. Remember, it goes L, ML. So what's our value of L then?
1.
1,
Yep. Our value of ML?
1.
1.
Yep. Okay, so that's important. So what do we do next?
Probably draw something.
What'd you say, Maddie?
Probably draw something.
Draw something. We don't have to draw anything yet. We can draw something
Gotta
eventually.
plug those into the wave function that you gave us some time ago.
Yeah, I gave you guys a sheet. Did I give you a sheet yet? Or at least it's on the back of your Quizlet. I'll put that sheet up.
The integrals maybe. But
Oh, that thing.
This thing. So we got to look in here. We got to find our function. So what's our function going to be?
minus plus. Why is it minus plus?
It's going to be
instead of
negative
minus
3/8
3/8?
pi 1/2 times sine theta e to the positive I phi.
Oh, wait, 3/8, my bad.
And then negative 3/8.
It's negative, right?
Yep.
Okay, what else do we got?
Times sine theta times e to the positive I phi.
Yep, that's it.
Wait, what's
Okay.
up with the minus plus in front of it?
So it's annoying because there's a plus up top. Whatever is up top stays up top. Does that make sense? So since it's positive 1, we get a positive value up top here. Or excuse me, we go with that negative value there, and we stick with that positive value up top. Does that make sense, John?
Not particularly, but we can go with it.
Okay. Yeah.
It's a negative three.
Basically, we're sticking with everything that matches with that plus, like the direction matters in this case.
Okay.
Any other questions?
It's negative 3.
It's
Eight.
negative 3/8. Yep. For the 1/2. Nope. Let's get back to where we were. There we go. Okay. So we have our wave function. What are we going to do now?
Solve it to see if it's equal to 1.
Right. So something's got to be equal to 1. What's equal to 1 in this case?
Conjugate
Mhm.
times the regular wave function.
Yep, complex conjugate times wave function over the integration. Okay. So what are our integration limits in this case? Or what's our function depend on?
Is it 0 to 2 pi?
Yep, we got 0 to 2 pi. And what's that for? Theta or phi?
That would be
Theta.
phi.
Yep. And then we got the other one, right? And what does theta go to?
0 to pi.
Yep. Okay. Complex conjugate of this guy. Tell me what's it going to be?
Negative I and the E term, everything else stays the same.
Yep. I didn't leave myself enough room. Ah! All right, what's our integration limits got to be?
Didn't we already?
Oh, I'm sorry. We need d what?
Pi and phi.
D
Yeah.
theta d phi.
Okay. On the next one, that should all be on the same line. If you couldn't get it, that's okay.
What's the order that you did it? Isn't it like the innermost integral corresponds to like the innermost like d part? Isn't so like
Yes, it should be switched.
It should
so
be
shouldn't it,
So we can switch it if you want to switch it. Doesn't
so it
matter.
would go like d. I remember it
Oh, I
mattering in like
s-
Calc 3. I wasn't sure.
In
And then
this case-
also like we wrote the integral backwards last, or we did it the opposite way where we had theta first and then phi.
Mhm.
Is that doesn't so why are we doing it this way, I guess?
Just to prove that we can, Maddie wanted to do it that way.
yeah,
What-
I'm gonna
Okay.
Oh, her right against the bus.
We're going to see in a minute why can we do it that way. So the question is does this sine function, does it depend on t at all? What does this part?
No, because it would cancel out because it's negative.
This part depends only on what?
Theta.
Theta. And this part over here only depends on what?
Phi.
Phi. So what do you think we can do?
Separate them.
Yeah, let's do that.
But isn't that term just gonna be 1, so it doesn't even matter?
It doesn't, but let's separate them out for now. Okay. Integral. Let's see. Let's separate them out. What terms only depend on phi here?
The EI.
Yep. IO. And on this farm, he had some quantum chickens. E-I-E-I-O.
Hear you.
You're such a dad right now.
That hurts. I gotta practice up, you know. I gotta make all my R-rated jokes like PG jokes.
Yeah, I guess you're right.
The hard task. So we got that first part, right? We can separate those out because these functions, they don't really depend on any other parts other than b, and we can pull out the other portion.
Is d tau supposed to have a sine theta with it?
I'm sorry, could you say that one more time, Ellie?
Is d tau supposed to have a sine theta with it?
D tau. Yeah. Oh yeah. There should be a sine theta in here. Whoops. We forgot it up here. Thank you. Good catch. So we got to squeeze in that sine theta for all of this stuff. So let's combine terms. What's the rest of this integral going to look like?
Sine cubed.
Yep. Sine cubed theta, d theta, and we're forgetting one more thing.
Just have the 3/8
Yep.
outside of it, really.
So -3/8 pi squared, or to the 1/2 squared. So really it just becomes
Right.
like 3/8 pi.
Yep, because we got that times,
Yeah, because whenever you multiply two radicals.
and like you said, this term becomes 3/8 pi, right?
Yep.
Okay. What's this term become?
2
Not
pi?
0. What is
2
it?
pi, right?
Yeah,
One.
overall it'll become
Oh,
2
yeah,
pi,
yeah,
but
yeah,
if I
yeah.
take e to the negative
No. I'll
I,
become 1.
yeah, this becomes 1. Okay. So let's write that out. We got phi 0 to 2 pi d phi times integral 0 pi sine cubed theta d theta times 3/8 pi. This integral, like you said, is pretty easy. What's the result going to be?
2 pi.
Yeah, 2 pi. This one, anyone know how to integrate this guy?
It's on the equation sheet.
You're darn tootin' it is. There we go. So, we're on tape. Yeah, working on dad stuff.
You're darn tootin'.
Shouldn't that be 3 pi over 8 as well?
3 pi over.
Because I don't think the pi was ever part of that fraction. It was just multiplied by the 3/8.
I'm not sure what you're saying, Josh.
I think because It's supposed to be like 3/8 times pi. I don't think it's 3/8 pi
3/8.
times
Oh, you
pi.
can-
times pi. So like your time would be up top, is what he's saying.
Yeah.
Oh, no, nope, it is 3/8 pi, like that.
Oh, all right.
Yep.
Yeah.
The way that this looks, it looks a little strange. So
Oh, so it is supposed to be
Oh,
like
yeah.
okay.
yeah, it's just crappy. Order of operations matters. You're thinking calculator language right now. Oops, I lost your paper. Okay. Yep, so Maddie is right. We can look this up in the table. I never remember it. Dx, this one's equal to -1/3k sine squared kx plus 2. That's all in parentheses. Cosine kx.
Mhm.
Okay. What's our k in this case?
Is it 1?
Yep, 1. So we don't have to worry about a ton of stuff. All right, so this first part, we know it's integration. We go from 2 pi minus 0, which is easy. The center part, get -1/3 sine squared theta plus 2 times cosine theta. We evaluate that from 0 to pi times 3/8 pi. Okay. We get 2 pi times -1/3 sine squared pi plus 2. Is that right? I lied. There should be another parenthesis there. Sorry.
Sine squared.
Yep. So you take the sine squared of kx first, then you
Just
add
kx, not the +2. Okay.
Then we got cosine pi minus -1/3 sine squared 0 plus 2 times cosine 0 times 3/8 pi. Okay, let's simplify some of this junk. What can we do with this 2 pi?
Simplify it with the 8 pi.
Yep. Pi goes away. Left over with a 4 there, right? Okay. Sine squared of pi.
One of those two are going to be 0 anyways, right?
Yep. This guy is 0.
Okay.
Cosine of pi.
1.
1.
Is it
Negative
1? -1. Right?
Yeah.
Let's
Sounds
double
right.
check. I think that's right. Let's double check it.
Because it starts with 0 is positive, negative would be pi over 2, and then pi would be -1.
Yep. You're right. -1. This part, sine squared is 0. Yeah, you're knocking it out the park today. Sine squared is 0.
0.
Yep. Cosine of 0.
1.
Yeah. All right. So let's see what we get. This portion is all multiplied together. So what? This term, the first part is 0, but there's that +2 there, right?
Yeah, okay. So that's, I see.
So it's negative 2/3. Well, no, it's positive 2/3 now.
Positive.
Because
Positive 2/3. Then we got minus.
where is it? No.
Yeah, you're
No,
right.
it's still not. Is it? Yeah, it is. It is. It is.
Because we got negative. Here, we'll simplify it.
Yeah.
We get negative 1/3 times 2 times negative 1 minus negative 1/3 times 2 times 1.
So now it's going to have to work out to
Okay.
4/3.
So
Oh, you figured it out.
yeah, you can guess what it's going to work out to. This whole portion, what's that become?
Just 2/3.
2/3.
Yep.
Thought it was a
Plus
triple.
this bit?
2/3.
Yeah. Times 3/4. So 4/3 times 3/4. What's that work out to be?
1.
1. Woo! So we proved it. Yes,
Forgot this was a proof. Yeah, that's right.
it
Great.
is normalized. So that's beneficial because any of the functions that you use on off of that sheet are normalized. So you don't have to renormalize them. You're good to go. Okay? All right. Let's talk about one experiment. So we found almost all the other quantum numbers, but we're missing one of them. Which one are we missing right now?
And
Yeah. Which one is it?
MS.
Yeah. Where the hell is MS? Okay. So to figure this out, this was determined experimentally, and it's kind of a cool story. So to do this, we have to look at the Stern-Gerlach experiment. Okay. The next question I'm going to ask you is going to seem completely unrelated, but it is related. What is the electron configuration of silver, a silver atom?
would you like the full or would you like the condensed?
You can give me condensed.
All right, so let's go with krypton
Mm-hmm.
and then 5s2,
Uh-huh.
and then 4d8 or wait, no, 4d9.
That's what you would expect. This is one of the
but-
weird ones.
So fill to 10.
Come on, John.
I know, I don't have those ones memorized yet.
So you were right with the energy levels of the orbitals, and which ones they were, but it's one of those irritating ones that has a 1s. The experimentalists behind this knew that the silver atom had a single electron in an orbital that was in the 5s. They knew that from other experiments and spectroscopy. Okay. So what they were trying to do is they were trying to show that there was quantization in this electron that was hanging around there, that it had a quantized spin to it. Bohr and his graduate students had hypothesized this, and they had gone through and done some theory to show that this was true, that the electron had to inherently have spin to it. So what they wanted to do, they wanted to try and see if this was true or not. So what they did is they got some silver, that's a little block of Ag. They put it into a furnace. They would heat it up really high, and they would get individual silver atoms. Okay. What they did next was they had a magnetic system in here. They where the field would remain somewhat consistent, north and south. And what they would do is the silver atoms would travel through that. And they had a detector on the end. Now, can you speculate what happened when they turned this magnet on and they fired these silver particles through?
With the detector on.
Yep, detector, yeah, with the detector on. Actually, the detector, they used a sheet of paper. They picked silver because you could see the silver atoms hit, and it was an easy way to detect that they were there. So what do you think would happen to this beam of silver atoms?
Maybe be in two spots on the paper, or would it form? Okay, let's go with fractured through the particle.
If you had a strong enough magnet, what would happen is you would get two parts. The fields would separate. And what they found is this one had a spin of negative h bar over 2. This one had a spin of positive h bar over 2. And this was pretty cool. So they did this experiment. I'm going to share you. Can you guys see my screen?
Mm-hmm.
Yeah.
Okay. So this was the postcard. They were so excited about their result, they put it on a postcard, Stern-Gerlach, and they sent it to Bohr. And what it says is, congratulations on confirmation of your theory. So this picture to the left, it's really grainy, you can't see it too well. These are silver atoms before the magnet is turned on. This is the silver atoms after the magnet is turned on. And what you can see is there's a spacing here once the magnet gets turned on. What's happening is the particles are being distributed a bit differently, and none are in the center. So really, our system should be turned on its side. The north and souths were on this end, and we found that the field splits these guys. So it was a pretty cool moment in history because they actually sent it through a postcard. They didn't wait till their paper was done. They were just that excited about it. Okay. So what conclusions do we have? Well, we have that spin itself of the electrons is quantized. So in classical mechanics, they would have gotten a broadband. In quantum mechanics, we of course would get discrete lines. So from this, we can actually see MS is there. There is some quantization there. Before we can truly find it, though, we have to approach actual atoms. Okay? Any questions about that? Josh, you look like you want to ask something.
Quantum, just love the spelling. Do you see? No, never mind. Quantum.
That's it.
Yeah, quantum. Yeah.
Reset.
Is that wrong?
Yes.
How do you spell it? Quantum. There we go. N. There we go. I'm a doctor.
Yeah.
Oh boy.
There we go. Spelling mistakes, man.
Josh, you're never gonna hack it in Maryland if you don't start making some spelling mistakes.
Yeah,
Come on.
yeah, exactly. Once you quit remembering how to spell basic things, then you'll be good to
That's
go.
how you know.
Yeah.
That's how you know you're starting to really learn something.
And if we're this bad, well, if I'm this bad at spelling, imagine my kid. Hopefully my wife takes it over.
Watch
Okay.
her be a national spelling bee champion.
Man, that would be, dance recitals and stuff are already bad enough. Imagine having to go to a spelling bee competition.
Spelling bee? Oh, I would be that really obnoxious parent.
Oh. It could be worse. She could be a football player.
First female kicker in the NFL, Dr. Simpson.
Yeah.
That's what it's looking
I'm hoping for Fortnite, man. Make a lot of money.
Jesus, yeah.
All right, so we're done with that stuff. Let's jump to chapter 9. We're going to move to a new chapter. And this is going to be all about atomics, spectra, and structure. Whoa, didn't mean to draw a line through that. All right. So we're actually going to talk about something real for once. Woo! All right.
Is it though?
It is. It's real. And we're going to start with the simplest atom. So what's the simplest one we got?
hydrogen.
Yeah. Specifically H1. So we're talking about a nucleus and electron. Proton, electron. Okay. Let's talk about the structure of the H atom. So what do we always do for quantum systems? The first question we ask, what does the Hamiltonian look like? For the H atom. Okay, so we have H hat. H hat's made of what two components?
Potential energy and kinetic energy.
Yep. So we got the potential energy operator and we have the kinetic energy operator. And then we have potential energy operator. Okay. And now we're talking about real systems now. So you guys will have a more inherent understanding of this system than we have in previous ones. I promise you. Chemical intuition is there. So we're going to ask the question, what contributes to the kinetic energy? And then we're going to ask afterwards, what contributes to the potential energy? Okay, so we're thinking about the H atom right now. What events contribute to the kinetic energy? What events contribute to the potential energy?
Kinetic
Mhm.
is velocity. Is that what you mean?
Yeah, it's related to velocity. So what's moving around?
Electrons.
Yep. So we got motion of electrons. Is that the only thing that's moving in this system?
The nuclear.
I feel like the atom might be moving
quarks
around.
too are technically moving a bit.
Motion of nucleus. Okay. Yep, so those contribute to the kinetic energy. What contributes to the potential energy then?
Everything else.
The position.
Yeah, which is what?
The position.
Energy.
I'm sorry, someone was saying something, but I couldn't hear him.
The position.
What do you mean by that? Can you be a little more explicit?
No, I can't.
How about the energy keeping the electrons in orbital?
Yeah, so what force is keeping that electron in orbit?
Coulombic
Considered
energy?
Coulombic, yeah.
Yeah, it's coulombic. So that's the interaction between what?
Electron.
Yeah, electron and nucleus. So
No.
electron nucleus interaction. And that depends on the electron nucleus distance. Okay, so let's try to rewrite our Hamiltonian. How are we going to rewrite that Hamiltonian?
Good question.
I'm guessing like the potential is gonna have to rely on R.
Yeah, we're gonna make it simple. We'll get to that in a little bit.
Okay.
So what would it be like? K equals V of the electrons.
Yep.
plus
So we got electrons. Well, in this case, we have electron, a single
electron. Okay, yeah, that's right. And then K of the one proton and one neutron together.
We're still gonna call that nucleus, though,
Nucleus, okay.
because it'll benefit us later on to use that language. And then what else do we got?
Plus V of the E nuke distance.
Yep. So the potential of the electron and nucleus, and that depends on R, we're gonna say. Okay. Let's look at these terms individually. We're gonna start with the last one first. Actually, we don't have a, oh yeah, we'll look at this one and then we'll be done for the day. Does that sound good?
Sure.
Okay. We've skipped around a lot in this class. So let's return to V hat electron nucleus. Okay. So this depends on, what are some things that electron nucleus interaction are going to depend on? There are three of them.
Charge.
Yep. Charge of what?
Both.
Yeah.
Okay,
Charge
so
of electron, charge of nucleus. Last one.
Distance of the two.
Yep. Distance between electron and nucleus. Okay. This is a special type of potential. Do you guys know what that potential is called? Starts with a C.
Coulombic potential.
Yep. Yep, Coulombic.
Jinx.
Potential. And therefore, Our operator is going to look like negative z, which is the nuclear charge, e squared over 4 pi epsilon r. What's z again?
The atomic number, right? Or isn't that like the charge of the atom?
Atomic number or nuclear charge. E naught. Epsilon naught, I'm sorry. Anybody remember that one?
Nope.
It's the permittivity of free space. What's E?
The charge of the electron.
Yep. And then that R is just that distance, right? The last question we're going to ask for the day. Question: why is there a negative sign? So
Has to do with why R is in the bottom.
What's that?
Probably because R is in the bottom. So as that increases.
I mean, like, why this negative value? Like, what does that mean for us? Is this an energy lowering or an energy raising interaction?
Probably lowering compared to kinetic energy, which is raising the energy.
Yep. This is an attractive interaction. Whoa, 3 T's, there we go. Meaning the energy is lowered. By this interaction. Because remember, if it goes lower, it's more energetically favorable. That makes sense, right? Positively charged particle, negatively charged particle, there's going to be some attraction. Okay, that's about all the time we have today. Are there any questions about what we talked about so far?
Nope.
No? Okay.